Hello, everyone. It is Saturday, the 18th of January, 2025, and this video, whatever you want to call it, the stream is going to be all over the place because for hours now I've been going down these rabbit holes, and yesterday as well I'm looking at sonar, looking at radar, looking at light waves, looking at sound waves, looking at frequencies like the visible and the non-visible light spectrum, and how light travels differently based on the modality that it's traveling through, or the whatever you want to call it, and how things like I've been saying now for years, temperature, pressure, and density are what makes up this Earth plane, using electricity and magnetism as the force that is utilized in order to create the visible and the non-visible light spectrum. I hope this all makes sense. And again, this is all dependent on how we experience this. Depends on all those things. And so, where am I going to start? So I wanted to get into this first. Whales, I said, I was just asking Google, how far can whales communicate using sonar? Whales can communicate using sonar over thousands of miles. Okay, and so I wanted to say that whales, they do, it's not significantly smaller of a circle than on the surface of the Earth that we inhabit, that we occupy, humans I'm talking about, but it's still a smaller circle. So things like the radius and the diameter and the circumference would be smaller. And so all very interesting. And so, and what are these sonar waves like curving with the alleged Earth curve that we have, and like going, like upwards of like 6,000 miles. Anyway, the distance whales can communicate depends on the type of whale, the water conditions, and the frequency of sound. So even ones that have teeth and not having teeth, also they communicate a little differently and use clicking noises and stuff like that, which also travel very far in water. Water conditions. The temperature and pressure of the water can affect how far sound travels. Frequency. Whales produce sound at different frequencies, which can travel different distances. For example, low frequency sounds can travel thousands of miles, just like light, right? But humans can't hear them. Type of whale, just like us, we can't see them. Like I'm talking about these infrared and radio waves that travel further distances. We don't see them, but we know they exist. Anyway, so it says here thousands of kilometers. Because low frequency sound travel further with less scattering, distortion, and transmission loss, baleen whales can communicate to each other over enormous distances, thousands of kilometers. Anyway, how far does whale sonar travel? Researchers believe that some of these low frequency sounds can travel more than 10,000 miles in some levels of the ocean. Sound frequencies are measured in units called hertz. The range of frequencies that whales use are from 30 hertz to about 8,000 hertz, and humans can only hear part of the whale's songs. Anyways, there's other animals too that also use sonar and things like that in order to communicate. And yeah, so that I'm going to close down to make sure that I don't reshare it. I'll get the videos. Where'd they go? Oh yeah, I was going to look at my history. Okay, so I'm going to look at wave refraction because this was very interesting.
Okay, one of the things.
And this is from Keith Meidel, and I started following him. Like his work, he is looking at this from like a globe. Well, I mean, he's actually looking at this like as a flat Earth plane of inertia, but he's someone that's not a flat earther. But anyway,
what we're going to be doing in lab is looking
at
what's
his expertise
called refraction, which is the bending of waves and their changing direction as they come into shallow water near shore. You may know that as waves move toward the shore, they create an orbital motion in the water, and that orbital motion dies out to nothing at a depth that we call the wave base, and that depth is equal to 1/2 of the wavelength of the wave. And so when waves come into water shallower than their wave base, they begin to feel the bottom. That orbital motion brushes against the bottom, and the waves begin to slow down. And that causes the waves to slow down and bend and change direction, which is the essence of refraction. For example, in this animation, you can see the waves in deep water are approaching straight, but they're going to slow down in the shallow water near the headland here, but still go fast in the deep water in the bays on both sides. And that causes the waves to bend and wrap and conform somewhat to the shoreline. That's what refraction is. And one of the things that's interesting about refraction is it's responsible for creating a lot of the famous surfing breaks that we see in Southern California and elsewhere. For example, this is Rincon Point up near Ventura, and the swells are approaching here straight from the Pacific Ocean, but they're slowing down in the shallow water near the point, but still going fast in the deep water out here, and that causes the waves to bend around. So by the time they reach here, you can see the waves changed its direction by about 90 degrees. So that's extreme refraction, and it creates a tremendous right break that's a famous surf spot at Rincon. Here's another example. These two little islands out near Hawaii, the waves are coming in from up here, and they're approaching the islands, and I've drawn the wave crests so you can see them a little bit better. And look at what happens. As these straight waves approach the islands, they slow down and drag in the shallow water near the islands, but they're still going fast in the deep channels away from the islands. And so they change from straight to rather radically bent. That's refraction. One of the things you'll be doing in lab is drawing what are called refraction diagrams, which is your prediction of how waves will bend and change direction as they come into different shapes of coastline. And so it's like you're up in an airplane, and we give you the starting waves here in deep water, and your job is to draw the wave crests showing how you think they're going to bend and refract as they approach the shallow water. You're always going to show them slowing down the closer you are to land where the water is shallower, but going faster where the water is deeper. And probably the easiest rule to remember is the waves tend to conform to the shape of the coastline. Not completely, but they tend to wrap to the shape of the coastline. Well, one of the interesting things about, oh, by the way, this picture here is a pretty good model. See where the land bulges out like this? That looks a lot like Rincon, doesn't it? So you can see it happens in real life right there. Okay, one of the neat things about refraction is that it can cause waves to bend their energy into one spot to make particularly large waves. And a lot of famous surfing waves are created this way. If a wave approaches the land straight, like the hand here, its energy is going to be spread out evenly across the coast. But if refraction causes the wave to bend concave in the direction that it's traveling, like the curved hand here, it's going to cause it to focus its energy into one spot, and that's going to tend to make a really big wave in just one spot. This is shown in this diagram here, where you can see an underwater ridge. These contour lines show an underwater ridge, so it's shallower water here and deeper water here and here. And as these swells approach, they're going to slow down over that ridge, but go faster over here. And that's going to tend to focus the energy right over the ridge and create a big wave right there where that X is. And this is the kind of situation we see at a lot of famous surfing spots. For example, this spot, some of you may recognize if you know about surfing waves, is Jaws or Piahi in North Shore of Maui. And a very large wave forms here just in one spot during certain northwest swells. It's a classic what's called an A-frame, where the wave just pops up in the center and is low on both sides. So it's kind of like the letter A. And the reason for that is that the waves wrap to an underwater, oh yeah, here's Laird Hamilton on the Jaws, on the Piahi wave. The waves wrap to an underwater ridge. It's shallow out here in this area, but it's deep over to the sides. And that means the waves start out straight, but they get more and more bent, more and more concave. And that focuses their energy into the spot right over the ridge, giving you both a left and a right break right over that ridge. Well, the wave you're going to be looking at is Mavericks in Northern California. And you're going to be trying to figure out why there's a big surfing wave that forms at one particular spot at Mavericks. Because again, you can see it's a lot like the Piahi wave. It's kind of an A-frame with just the big wave right in one spot. So on a big day at Mavericks, there's a reason why the waves form there, and you're going to figure out why. It has everything to do with refraction.
Okay,
Hi, oceanography students. Okay, one of the things we're going to be doing in
this one was very interesting.
One of the important things our atmosphere does is control how much precipitation falls on Earth.
And it's the same guy, same channel.
Precipitation is just water that comes down from the sky. It could be as rain, it could be as snow, it could be as hail, any other form you can think of.
So just water.
Some places on Earth have lots of big wet climates. If I was doing this in Seattle or Vancouver, I probably want an umbrella right now. But I'm in San Diego and it's another typical day here, blue skies, no rain. Why is that? Why is it that some places on Earth have lots of precipitation, whereas other places tend to be very dry climates? Turns out it's a pretty simple reason. It has to do with whether the air is mostly rising upward or mostly sinking downward. I'm going to draw a quick sketch for you on the board of how our atmosphere circulates. What you can see here is this diagram of the globe with the North Pole up here and the South Pole down here and the equator in the center, and then 30 degrees north and 60 degrees north latitude, 30 degrees and 60 degrees south latitude. What we find is that the equator is the place that receives the greatest amount of solar energy on Earth. The sun shines at a high angle there and really heats the atmosphere. And so the air tends to get very warm and it tends to expand and become less dense, and so it tends to rise. And I'll just show that by showing arrows showing the air rising upward, okay? This is just going to be a two-dimensional view of something that's happening over the whole planet. So right here, for example, the air is rising out of the board towards you, okay? What happens to this rising air is it tends to turn and head toward the poles, both to the north and the south, and then by the time it reaches...
So look at this as a top-down view of the Earth. So even if it was a globe or a sphere or a half sphere or a cylinder or a cone or a plate, it would still be for the two-dimensional base, it would still look like this top-down view with the and so I found this very interesting because when I overlay the sun's travel path through the equatorial belt and then the Tropic of Cancer and the Tropic of Capricorn, I do see parallels to the areas that are drier and the areas that are wetter and colder and hotter. And so this also is very interesting to me that and even the way he shows where the air or the ether like forms these waves in the air. It these are in areas where there's like more cyclones, there's more hurricanes and tornadoes and things like that. So that's also very interesting to me that even on the luminary's travel path, there seems to be like interruptions within the atmosphere that, and again, creates like these high wind events and things like that. And so I did want to show just an image just so people can see what I'm talking about. And so you see here, I wanted to make it more expanded, but it shows like the equator, Tropic of Cancer, Tropic of Capricorn, and then that's again like the sun's travel path, 23.4 degrees south latitude, Tropic of Capricorn, and then 23.4 degrees south latitude is the Tropic of Cancer from the equatorial belt, which is 0 degrees. And then so like a little bit higher, for example, would be like the 30 degrees that he's talking about. A little bit higher than that would be like the 60 degrees that he's talking about. And then again, north and south would be the same thing would apply. So this is 23.4 degrees south latitude. A little bit lower than that would be the 30-degree line. And then like around this area here would be the 60-degree, like further down here, because that's still Patagonia, South America. Anyway, and so very interesting, very interesting. And if you look at the inverse square law as well, like you'll see that the sun necessarily would be smaller and more localized, more local than and within the contained environment. So carrying on with him is so friggin' interesting.
Which is about the 30-degree latitude belts, it becomes cooler, and so it tends to contract and sink back to the surface of the Earth. And some of that air heads back to the equator, and some of it heads away from the equator toward the poles. Now, at the North and the South Pole, it's kind of the opposite happening. The air is very cold, and just as hot air expands and becomes less dense and wants to go up, cold air pulls together and becomes heavier and wants to sink. So the air tends to sink near the poles, and what will happen is it doesn't really have any choice but to try to go toward the equator. Again, that's happening all over the place. I'm just doing this in one part of the diagram. So the air sinks and moves toward the equator.
Oh, come on.
In both the north and the south. And what happens is this air ends up colliding with the other air that's heading toward it along what we call polar fronts. And it forms other somewhat less well-developed circulation cells. Okay, but the key thing that we can notice when we sketch out the atmosphere like this is that we can recognize specific belts, regions where air generally tends to rise or where air generally tends to sink. And this turns out to relate very closely to how much precipitation we get. The equator, which is where the air is rising, turns out to be a very wet climate. More rain falls in the tropics along the equator than anywhere else on Earth. Where the air is sinking at around the 30-degree north and 30-degree south belts, those tend to be our dry climates. If you look at an atlas of the world and look where the big deserts are, like the Sahara and the Kalahari deserts or the great deserts of the southwestern United States, you'll see they sit along that 30-degree belt. As we move up to about the 60-degree north and south belts, we tend to get wetter climates. So this would be, for example, northern Canada or Alaska. And then as we move to the poles, we actually have areas of sinking air, which correspond to mostly dry climates. I know that might seem strange because there's all this snow at the poles, but the net precipitation, the amount that it snows every year at the poles is actually very little. It's so cold that that snow tends to stick around. So where we have areas of rising air, we tend to have wet climates. Where we have areas of sinking air, we tend to have dry climates.
You can see these patterns on a satellite image of the Earth. Look at that band of clouds right along the equator where the air is rising. Go north and south of there to those bands of clear skies where the air is sinking. North and south of there, you see more clouds in the 60-degree latitude belts where the air is rising.
Oh my God, I just got to go back to that because again, like this is like, even with CGI.
North and south of there,
look at the land mass. Okay, like that's only one continent. I believe it might be Africa. Correct me if I'm wrong. But anyway, doesn't matter. One continent out of the multiple continents that we have, and you have this on like 50% of the globe, right? And so the remaining continents like North and South America and Asia and like all no, we're not gonna look at that. Okay.
You see more clouds in the 60-degree latitude belts where the air is rising.
Okay.
So let's figure out why it is that areas of rising air tend to have high precipitation, whereas areas of sinking air tend to have low precipitation. Well, in my diagram here, what I'm showing is that if you have an area of air near the surface of the Earth that begins to rise, what happens is it expands. And the expansion means that the air cools down because the molecules in the air are not fighting for as much space. The same number of molecules is spread out over a smaller area, a larger area, and so they don't bump into each other as much, and everybody slows down, and that means the temperature drops. When the air cools down, it becomes easier for any water molecules that are in the air to get together with each other. The water molecules will hit each other, and they're electrically attracted to each other, and so they'll tend to gather. And if they form drops that are big enough, the drops begin to fall out of the sky. So areas of rising air expands and cools down, and you'll tend to get higher precipitation in that area. It's very important that you have an accurate diagram when you do this. So I need an umbrella here for my little guy because it's raining. In areas of sinking air, we've got the opposite situation happening. If air high up in the atmosphere sinks down toward the surface of the Earth, it tends to squeeze together because there's more weight of the atmosphere on top. And so it's squeezing it together. When you compress the air, it tends to warm it up because you're crowding the same number of molecules into a smaller space. So they start bumping into each other and everybody starts vibrating and moving faster. And that means it's getting warmer. When you do that, all those air molecules zipping around means any water molecules that get together get knocked apart. And so it's very hard for water molecules to form drops in that situation. So areas of sinking air where the air compresses and warms up, those tend to be your dry climates, areas of low precipitation. Here you're going to want to have not an umbrella, but a hat because it's sunny. This device here will help me illustrate these points I've been trying to make. This is called a cloud maker. You can see it's a glass bulb and there's water there in the bulb. And even though we can't see the water molecules in the air, we can be pretty confident that the air in here is very humid. But there's no cloud there. There's no rain.
Notice he needs a contained environment.
Well, in the atmosphere, when clouds start to form, what happens is the water drops typically try to nucleate around little bits of atmospheric dust. And we're going to mimic that here by I'm squeezing the bulb and squeezing some air out and clamping the tube. And I'm going to suck a bit of smoke in to mimic the kind of dust that you might get in the atmosphere where you might get a cloud to form. How about, there we go.
It's heat.
Okay, so we're going to suck a bit of smoke in. And then when I squeeze the bulb, that's mimicking what happens in areas of sinking air. You squeeze the air and it warms up and you don't tend to get a cloud to form. But watch what happens in the bulb when I let the pressure off here. When I let the pressure off, you see how a cloud forms. Water molecules are able to get together because the expanding air cools and allows them to condense around little bits of dust. Squeeze the air and the cloud goes away. That's like air sinking toward the surface of the earth, compressing and warming. Let the pressure off the bulb and a cloud forms. That's like air rising, expanding, and cooling. So in areas of the earth where we have sinking air, we tend to have low precipitation. In areas of the earth where we have rising air, we tend to have cloud formation and high precipitation.
That was so interesting too. I hope that you're enjoying this.
Did you ever wonder why the Earth has high places and low places? We've got these places called continents that stick up out of the ocean, sometimes miles above sea level. And then these other areas that we call ocean basins, which lie on average 2 to 3 miles below sea level. And there's not a lot in between. High places and low places. Why is that? It's unusual among the planets that we know. Well, it turns out it's because the Earth is made of two very distinct kinds of crust, what we call continental crust and oceanic crust. I've got here on the board a generalized sketch of the continental crust and the oceanic crust. And the two kinds of crust lie on this very thick region of the Earth beneath that we call the mantle. And that extends down to about halfway down to the center of the Earth. You can see on my sketch that there's one very clear difference between the continental crust and the oceanic crust. The continental crust is a lot thicker. It averages in thickness about 35 kilometers, which is about 22 miles, whereas the oceanic crust averages only about 8 kilometers in thickness, which is about 5 miles. So there's a big difference in thickness. There's another important difference, which is in their density. I'll show you in a minute the kind of rock that makes up the continental crust, rock like granite and its relatives. And that continental crustal rock is
again, I'm just going to point out the obvious here, okay, that this is flat over thousands of kilometers, possibly like in this illustration, or at least hundreds of kilometers. And everyone's representation, it's flat. There's no curve. There's no fucking fudging bend. Sorry for swearing. Of the oceanic crust versus the continental crust. And the mantle could possibly be, again, what contains all of this, right? And I do want to get into it because you talked about rock, this being rock, but wood turns to rock. Wood turns to stone. And so I do believe that it's possible that what makes up this stuff and below is possibly like the deep root structure of a petrified tree or trees. And we see that all over the world. Like, I know this sounds crazy to people, but you see like these large mountain chains and stuff like that. And this could possibly also be petrified trees that possibly rotted and petrified that way and broke down and stuff like that. But yeah, anyway, I'll let him keep talking.
Relatively low density rock. Its average density is about 2.7 grams per cubic centimeter.
And I've talked about this like before also, like he's talking yet again how temperature, pressure, and density matters literally in the land, air, and sea. And when he talks about the air, this is the ether. These are gases that comprise the atmosphere, whatever you want to call it, like nitrogen and oxygen and helium and hydrogen and carbon dioxide, et cetera, et cetera. And depending on things like temperature, pressure, and density, It's whether they are above us or below us or with us on this within this cosmos. I hope this makes sense to people. And so like even with things like ionized gases being plasma and possibly being like another state of matter, we do need to look at things like solids, liquids, gases, and plasmas, and how these are all just essentially, again, like the elements in various forms utilizing various energies, whether it be more electrical and gravitational, or whether it be more radiating magnetic nuclear, centripetal versus centrifugal, positive versus negative, electrical versus magnetic, pushing versus pulling, all of that stuff.
If you're not familiar with the metric system, think about water and how heavy a gallon of water is. Water is about 1 gram per cubic centimeter. And so the continental crustal rock is about 2.7 times heavier for a given amount than water. The oceanic crust is made of different minerals, and the rock there is a little denser than the granite, about 3 grams per cubic centimeter. In other words, it's about 10% denser than the continental crust. And the mantle rock upon which both of these crusts lie is the densest of all. It's about 3.3 grams per cubic centimeter up in the upper part of the mantle, and gets denser as you go farther down. And that turns out to be an important difference. The continental crust is the least dense of the three, and both of these kinds of crust are less dense than the mantle. And as I'll show you in a minute, both kinds of crust actually float in this heavier, denser rock beneath them that makes up the mantle. I have here a piece of granite. This is the main rock of the continental crust. You can see that it's light in color, although it's got some darker minerals in it. And you may be able to even see from there that the minerals in it are visible. They're about the size of peppercorns or so. So it's what we call coarse-grained, big minerals. And this is a fairly low-density rock, and it's the main rock that makes up the continental crust. In contrast, I've got here a piece of volcanic basalt from the ocean floor. This is the main rock of the oceanic crust. You can see it's dark in color, and also the crystals are much tinier. As I run my fingers over the surface, I can feel more like a sandpaper texture. So peppercorn-sized crystals versus sand-sized crystals. And this is the most common rock on Earth, really, because it forms from volcanic eruptions at mid-ocean ridges as the seafloor spreads and grows. This stuff, volcanic basalt, paves the entire bottom of the ocean floor. You can also see it on islands like Hawaii. It's the same basic kind of rock, but it's the most common rock on Earth. Between these two rocks, the basalt that makes up the oceanic crust and the granite that makes up the continental crust, we've got most of the rocks on Earth covered right here. In this demonstration, this pan of water represents
oh yeah, no, he's going to talk about
Earth's mantle.
He's going to show what
now, the Earth's mantle is not actually liquid molten rock. It's solid, but it's so hot that over long periods of time, it does behave somewhat like a liquid in that it moves and deforms.
Anything, it would be colder. And so he's going to talk about wood. I'm getting ahead of myself here. God, I didn't even wash my face this morning. I feel gross. Anyway, yeah, I guess I'll just share this with you. This is a periodic table of elements. And you've got them all in here, which makes up this earth plane. So when you look at oxygen and nitrogen and the different noble gases and how they interact to make light. Anyway, that's not what I wanted to show you. Petrified wood, trees that turn to stone. This was from February 2017. While most fossils are merely impressions of the original plant or animal life that made them, petrified wood is essentially a three-dimensional representation of the original tree. Though none of the tree's organic material actually remains in the petrified wood, the original structure of the tree itself is preserved down to the finest microscopic details. It is often possible to observe structures such as tree rings in the petrified wood. And I've actually showed petrified, well, what is rock, but that has knots in it, right? And so I do believe it's pine, petrified pine, that turned into stone. And that was in Red Rock area, or maybe it was Phoenix Point. Anyway, in Arizona. No, in Nevada. The petrified wood can take on various colors depending on the type of minerals which were present during the petrification process. I believe it depends on the sap or the blood of the tree that it also impacts the color. Petrified wood in BC and Alberta. Anyway. Is your yard full of dead or dying trees that you're hoping might turn into petrified wood one day? As cool as petrified trees and petrified forests are, the process of petrification takes millions of years. Again, I don't buy that. Don't buy that. We don't have like accurate carbon dating or dating in order to even accurately predict that beyond even like 25 to 50,000 years. Where's the other one I had on petrified wood? No, there we go. So these are different types of petrified woods. They're calling it a fossil. From fossil to your countertop, all about petrified wood. What is petrified wood and how does it form? Petrified wood is a special type of fossil, its name meaning wood turned into stone. Formed over millions of years. Again, I don't buy that. When plant material is buried by sediment and protected from decay by oxygen and organisms. Petrified wood undergoes a process known as permineralization to become a fossil. Groundwater rich in dissolved solids flows through the sediment, replacing the original plant material with inorganic material. The result is petrified wood, a plant with its basic structure replaced by stone. Uniquely and rare conditions must be met for a log to be transformed into petrified wood. What can be found? Large forests and fields of petrified wood have been found in many areas of the world, from Australia all the way to North America, including the western states of Arizona, Wyoming, Utah, and Colorado. One of the most well-known collections of petrified wood is located in Petrified Wood Forest Park in northeastern Arizona. Today, park visitors can observe by collecting any specimens. But collecting of any specimens is prohibited. How does petrified wood become a stone slab? Petrified wood suitable for a stone slab is hand-selected and brought back for careful inspection. The chosen fossil must be generally free of any fractures or cracks in order to be suitable for a slab. Petrified wood logs are then individually cut and bound with a resin, transforming into a slab through a combination of Mother Nature and highly skilled craftsmanship. Exotic minerals found in the make of this specimen. Anyway, just again, petrified trees, stone, rock. I know how that sounds. Is this the one?
Represent my two kinds of crust. I've got two blocks of wood. This first block of wood is a piece of redwood, and if you know anything about redwood, you know it's a fairly light, low density type of wood. And you can see I've cut this block to be quite thick. So this represents my continental crust, thick and low density. And then here I've got a piece of cherry. Cherry is a hardwood, and so it's a denser wood. And I've also cut the piece to be thinner. And so this thin, higher density block of wood represents my oceanic crust. And when I float my continental crust in the mantle, you can see it sits up high. And when I put my oceanic crust into the mantle, you can see that it sits down low. So the thick, low density rock of the continents floats high enough in the mantle to stick up out of the ocean and form dry land, whereas the thin, high density rock of the ocean.
Notice he didn't mention gravity at all.
Floor sags down low in the
There
mantle.
are such things as gravitational forces and radiating forces, but again, like this 9.8 meters per second squared, like downward acceleration is not a thing.
To sit several miles below sea level. If we didn't have any of this stuff on Earth, rocks like granite forming thick, low density rock, there would hardly be any dry land on Earth. We would be a planet completely covered by ocean water with maybe just a few islands poking out. And so every day I hope you do what I do, which is to thank the thick, light rocks of the continents for floating high in the mantle and forming dry land, because otherwise we wouldn't be here talking about it. Now, in fact, I don't actually thank the continental crust every day, but you do get my point, right?
Yeah. So again, very interesting. I hope you are enjoying this because I absolutely did. Let's see. Okay, I'm going to shut that down. I'm going to read you some things on sonar. and radar. Okay. Sonar and radar are both remote sensing technologies that use waves to detect and locate objects. Sonar uses sound waves to detect underwater objects, while radar uses radio waves to detect objects above sea level. How they work. Sonar emits sound pulses and detects the echoes that bounce back from objects. Radar emits radio wave pulses and detects the echoes that bounce back from objects. Applications. Sonar, used in underwater exploration, fishing, diving, and military operations. Radar, used in navigation, collision avoidance, weather pattern identification, military operations, and air traffic control. Differences. Speed. Radar waves travel faster than sound waves. So radar systems can detect objects faster. Range. Radar has a longer range than sonar. Environmental factors. Sonar performance is affected by water temperature, salinity, and turbidity, while radar is less affected by environmental factors. So Canadian physicist Robert William Boyle developed the first practical underwater active sound detection apparatus in 1917. Sonar stands for sound navigation and ranging, and radar stands for radio detection and ranging. As their name suggests, both are used for navigation and detection of different properties and attributes of objects. All right, what else did I? I'm searching through a lot of things. Yeah, so sonar, again, how whales communicate and other underwater beings. What was this? Sound waves by frequency. Sound waves are classified, which is the number of cycles of a wave per second. Sound waves with higher frequencies are perceived as higher pitched sounds, while lower frequencies are perceived as lower pitched sounds. Frequency ranges. Infrasonic sounds with frequencies below 20 hertz, which are too low for humans to hear. So there's the visible and non-visible light spectrum, and there's the like the hearing and the non-hearing sound spectrum for humans that we have, which is and again, even with the visible and audible parts of both, we're very limited to what we can actually perceive as humans, and but it still makes up, again, this cosmos, this universe. Anyway, audible sound with frequencies between 20 hertz and 20,000 hertz, which humans with normal hearing can hear. Ultrasonic sounds with frequencies above 20,000 hertz, which are too high for humans to hear. Frequency and other sound wave characteristics. The distance between two peaks of a sound wave. Lower frequency waves have longer wavelengths. Amplitude. The height of a sound wave, which is often measured in decibels. Larger amplitudes produce louder sounds. Standing waves. A phenomenon that occurs when two waves with the same frequency travel in opposite directions. Standing waves are important in the design of musical instruments and architectural acoustics. High frequencies produce more oscillations. The units of frequency are called hertz. Yeah, so then they get into middle and low and high. Five main characteristics of sound waves: wavelength, amplitude, frequency, time period, and velocity. The wavelength itself is a longitudinal wave that shows the compressions and rarefactions of the sound wave. Yeah. Anyway, that was interesting. Again, I'm just sharing this information just in case it helps like piece the puzzle together. Nope, that's me. So every time I asked about the speed of light, they were always giving me the speed in a vacuum, and so I was getting annoyed. So I'm like, does light only travel in a vacuum? I was being sarcastic. And so anyways, no, light can travel through a vacuum and through matter. Anyways, I don't know about the vacuum, but I know through matter. Light, because that's what makes up this Earth plane, right? Like light travels through, anyways, Earth. It's made of matter. Anyway, light is an electromagnetic wave that can travel through empty spaces like the vacuum of space. Anyway, they keep on saying this stuff. Light can also travel through materials like air, water, and glass. Like, this is more important, right? So I'm going to talk about light and matter, because again, they always push the light in a vacuum shit, and it's really annoying. But light and matter, because again, that's what applies to us on this earth plane. Light travels more slowly in matter than in a vacuum. The amount it slows down depends on the materials it's traveling through. For example, light travels more slowly in water than in air. Light in opaque materials. Light can't pass through opaque materials like metal because the atoms absorb some of the photons. Light in transparent materials. Light slows down when it passes through transparent materials like glass and water. Some of the light is absorbed and lost as heat. Yeah. And light it bends. It doesn't curve like, like it's a sharp bend. Anyway. I'm being very slow with this, sorry. So yeah, like I've already talked about this stuff. Like I shared with my conversations with ChatGPT regarding like photons, protons, electrons, ionized gases, and the removal of electrons with light. These radiating particles, or whatever you want to call it, just like the sun's rays. But anyways, I like to go through it again. Light travels through matter in a variety of ways, including being absorbed, transmitted, reflected, or refracted. Absorption. Light transfers its energy to matter and is transformed into heat energy. Transmission. Light passes through matter such as transparent materials like glass. Reflection. Light bounces off matter such as in snow, which reflects all colors of visible light. So again, I consider lasers to be light, like radiating energy. Anyway, light bends as it passes through matter. I'll show you how it bends again, because they keep on using the same terminology to kind of like reinforce this indoctrination of what they're trying to like make us perceive the world to be. Scattering. Light scatters as it passes through matter, which can make objects appear glossy. Transparent, translucent, and opaque materials. Transparent materials that allow light to pass through easily, such as glass. Keep on bringing up glass. Materials that allow some light to pass through, but scatter some wavelengths of light, such as wax paper or glass blocks. Opaque. Materials that do not allow light to pass through, such as bricks or books. Light's behavior in matter is predictable and specific. For example, light can be emitted by matter, such as when, see, they keep on getting into this stuff, such as when stars, galaxies, and light bulbs glow. Sure. Yeah, light travels in a variety of ways when it comes into contact with water, air, and other matters. It is absorbed, transmitted through, reflected, and scattered. Yeah. Same stuff. Yeah, so I've gotten into this stuff as well. Anyway, I want to get into a flat earth video. I'm going to keep on looking at light and how it can be impacted by things like light, temperature, pressure, and density. Looking at freezing it again. This is the one. Right here. I haven't seen this one yet, but I want to...
Here's a way you can prove the flat earth irrefutably. The Suez Canal. This engineering marvel is over 120 miles long and completely level the entire way. No dips, no drops, just straight flat water. Now, if the Earth were truly a globe, we'd expect to see some sort of curve over that distance, right? So why is it perfectly level? Let's dive deeper into this. You've got this massive canal connecting the Red Sea to the Mediterranean, allowing ships to travel in both directions with ease. But if we're really living on a globe, shouldn't there be at least a little drop-off along those 120 miles, even just an inch? That's what you'd expect if the Earth curved, right? So why is it completely flat? In fact, here's a little experiment for you. The next time you fly, try recording the entire flight. Just let the camera run and notice something. There's no curve. The plane doesn't dip. You don't feel yourself nosediving to compensate for the Earth's curvature. Even better, ask the pilot if they have to account for the Earth's curve while flying. Most likely they'll look at you and say no. And let's be honest, if gyroscopes don't account for curvature, then why should we? But let's not stop there. Let's talk about emergency landings. If you look at flight patterns and emergency landings, you'll notice something odd. They only make sense on a flat Earth map. You know, the one that looks an awful lot like the United Nations logo. On a globe, these landings are way out of place. It's almost as if the Earth isn't a spinning ball, but a flat plane, just like some of us have been saying all along. And water, let's think about that too. When you spin water in a bucket, does it form a ball? Nope, it convexes outward. It does the complete opposite of forming a sphere. Water seeks its level, it doesn't curve around a ball. It's in the very nature of how fluids behave. So why would we think oceans are bending around a globe? It just doesn't add up. If all of this is true, why would anyone lie to us? What's the most?
And so I just wanted to clarify like why I'm talking about things like light versus sound, in what and in which environments they function more effectively in, and where also with electricity or versus magnetism, gravitational forces versus radiational forces, how they function more effectively above sea level versus below sea level, like these discussions. And so like with things like sound waves, they function more effectively at like within the water, within the sea, and light functions more effectively above sea level. And so even with that, like we need to look more into that and the distances that are traveled.
Motive behind convincing us we live on a spinning ball when in
straight, anyways, in a straight line.
fact the Earth is flat. Well, let's talk money. Space exploration is $1 trillion industry. NASA alone rakes in $69 million a day, every single day, from your tax dollars. To put that in perspective, that's more than what all the McDonald's in the world make in a day, and you can Google that if you don't believe me. The truth doesn't need to lie to win, it just is. But lies need your belief. They need your participation to exist. So why is the globe theory constantly pushed while the flat Earth idea is ridiculed? Maybe it's because the truth of our world is something they don't want us to see. Maybe they don't want us questioning the status quo.
If the Earth is a spinning globe, why can't NASA just zoom in and show us people driving upside down in Australia? NASA claims to have thousands of satellites orbiting the planet, capturing endless data and imagery. If that's true, shouldn't it be the easiest thing in the world to show us what life looks like on the bottom of the globe? Picture it, cars zooming along upside down, or surfers riding waves that are apparently hanging beneath the Earth. But we never see that perspective. Why not? With all the technology they boast about, where's the live footage of this so-called upside-down world? Here's the alternative explanation that makes more sense. The Earth isn't a spinning ball at all. Instead, it's flat and stationary. That would explain why the horizon always looks perfectly flat, no matter how high you go. It also explains why airplanes maintain a level flight path without dipping their noses to account for a curve. Everything we observe aligns far better with a flat Earth than the spinning globe story we've been told. And it doesn't stop there. Have you ever looked closely at NASA's space footage? There are documented instances where astronauts appear to manipulate camera angles or obscure windows to create the illusion of a spherical Earth. One infamous clip shows astronauts using a small circular section of a window to simulate the view of Earth from deep space. But when analyzed, it's clear they were still in low Earth orbit. Then there's the moon landing. NASA itself has admitted they've lost the technology to return to the moon. How do you lose something so monumental? It's like saying we forgot how to build pyramids. These inconsistencies raise serious questions about the entire narrative. So what do you think? Could the flat Earth model make more sense than we've been led to believe? If the Earth is a spinning globe, why can't NASA just zoom in and show us people driving upside down in Australia. NASA claims to have thousands of satellites orbiting the planet, capturing endless data and imagery. If that's true, shouldn't it be the easiest thing in the world to show us what life looks like on the bottom of the globe? Picture it, cars zooming along upside down, or surfers riding waves that are apparently hanging beneath the Earth. But we never see that perspective. Why not? With all the technology they boast about, where's the live footage of this so-called upside-down world? Here's the alternative explanation that makes more sense. The Earth isn't a spinning ball at all. Instead, it's flat and stationary. That would explain why the horizon always looks perfectly flat, no matter how high you go. It also explains why airplanes maintain a level flight path without dipping their noses to account for a curve. Everything we observe aligns far better with a flat Earth than the spinning globe story we've been told. And it doesn't stop there. Have you ever looked closely at NASA's space footage? There are documented instances where astronauts appear to manipulate camera angles or obscure windows to create the illusion of a spherical Earth. One infamous clip shows astronauts using a small circular section of a window to simulate the view of Earth from deep space. But when analyzed, it's clear they were still in low Earth orbit. Then there's the moon landing. NASA itself has admitted they've lost the technology to return to the moon. How do you lose something so monumental? It's like saying we forgot how to build pyramids. These inconsistencies raise serious questions about the entire narrative. So what do you think?
They raise questions, which is absolutely right, and we should keep on continuing to look at that. Let me see here. There's a lot of good videos in here. Law of the Luminaries, I was really interested in that. The astrolabe, I do have an astrolabe, the original supercomputer for this divine clock. Law of the Luminaries. Maybe I'll show one part. I don't know what this is about.
This is the first video in my 144 series, and I'll explain why I call it that in just a minute. Today is November 3rd, 2024, and I'm going to show you the proper new moon and how the moon moves through a lunar month in relation to the sun. Print this up and you can follow along. And then I'm going to show you.
Before I get into this stuff, I do want to look at it first, because a lot of people do get it wrong, these travel paths. But I mean, she's right about the predictability of the full moons and the new moons. So for example, in one month, if the full moon was in Capricorn, the following month it would be in Aquarius, and then it would be in Pisces, and then it would be in Aries, and then Taurus, and Gemini, Cancer, anyway. And same thing with the new moons. If a new moon was in Gemini, for example, then the following one would be in, after Gemini is Cancer, and then Leo, then Virgo, then Libra, then Scorpio, anyways, and so on. I did want to see this video though, because again, this is based on a globular Earth model, but at least, you know, when you look at it two-dimensionally, it's a circle, whatever shape you believe this Earth to be. And anyways, flat is not a shape. I haven't watched this yet, but I'm going to watch it with you.
Every place on the surface of the Earth has a latitude and longitude. These are the coordinates we use to locate each point on the Earth's surface. Just like how you plot points on a graph with an x and y value, you can plot points on the Earth
Temperature and
using
pressure.
the latitude and longitude. Latitude is the angular distance of a place north or south of the Earth's equator in degrees. A latitude of 0 degrees is on the equator of the Earth. We'll talk about that later. 90 degrees north is the North Pole, and 90 degrees south is the South Pole. Longitude is the angular distance of a place east or west of the meridian at Greenwich, England. A longitude of 0 degrees means it's directly north or south of Greenwich, England, and a longitude of 180 degrees west means it's halfway around the world from Greenwich when measured east to west, ignoring north to south. With these two numbers, any point on the Earth's surface can be located. One way to remember which is which is to remember that latitude is like a ladder, because you use them to move up and down. Lat and lad sound the same. and longitude is the other one, left to right. There are two types of key lines we draw on our maps of the Earth. Longitude lines that go north to south are called meridians, and latitude lines that go east to west are called parallels. In today's lesson, we're going to talk about a few of the most important parallels we draw on the Earth: the equator, the Tropic of Cancer, and the Tropic of Capricorn. The equator is one of the Earth's parallels. It's a line where everywhere on that line has a single latitude. In the case of the equator, this is a latitude of 0 degrees. Every latitude on the Earth is measured north or south from the equator.
That was interesting. Oh my goodness, so many other things I wanted to look at. But anyways, I won't. I will not. So what did you think of that video? Is there anything that you think that I should look at more closely? Something that I'm missing? If you want to refer me to other people that discuss this type of stuff. So yeah, it's snowing here, kind of stuck in. Feel like I'm hibernating. There's people in like Greenland and Norway and like the more northern regions where they sleep like at least like 14 hours a day, and like they're in these like little communities, and they stay inside mostly for the majority of the time during the winter months, with the exception of like I guess going out and getting wood for the wood stoves and stuff like that, and feeding their animals, but like mostly inside. And so that's what I'm doing, being that I'm in Ottawa, Canada. Anyways, on that note, I will leave it at that, and I hope that everyone has a wonderful rest of your day.